All right, I have 10:05 on my clock. I want to go ahead and get started, just out of respect for everyone's time. We still have a few people joining in, so as they come in, I'll accept their invite to join. But I want to thank everybody for coming out today. As you can see, we're going to talk about atmospheric hazards within confined spaces. Now, this is something that I've got different types of experience with. You'll see from my background as from the fire department, you will be able to see my confined space rescue experience, my experience from the EHS professional to where we're making policy procedures. Hopefully you can take some things back to your employer, your organization, and apply those things and hopefully make best practices out of your industry. If you have questions throughout, feel free to speak up, but we will have a Q&A session at the very end. And then as a reminder, we will send out a certificate of training to everyone that's in the training today. So I'll email that to you. You should have that by the end of the day. So we'll go ahead and get started. Again, feel free to chime in if you have questions. You don't have to wait till the end if you don't want to. Feel free to chime in and we'll make it as interactive as possible. So what we're going to discuss today is things that you may not understand within a confined space pertaining to atmospheric hazards. So if you're dealing with confined spaces, whether it's in general industry, whether it's in construction, whatever environment you're in, there are some things that you want to understand that your gas meter, your portable gas detection equipment, whatever you want to call that, some things that it may not be telling you that you have to understand and interpret so that it can keep you safe within the workplace. So give you a background about myself. 15 years as a environmental health and safety professional. I'm currently the president and CEO of Aero Safety. It's a safety consulting firm based here in Kentucky. And as I mentioned previously, I did over 10 years as a career firefighter, EMT, hazmat specialist, confined space rescue technician in Louisville, Kentucky. That's where I got a lot of my experience from the rescue standpoint and a lot of my initial experience from the confined space atmosphere as general. EMT, I'm a current EMT for the Kentucky Department of Medical Reserve Corps. And so I do that as a volunteer status. We get called out from time to time to help out with whether it's COVID-19 issues or certain disasters that go on. Educational background, I have a master's in occupational health and safety from Columbia Southern, currently as a PhD student at Capital Tech University. And then I serve on several professional committees within CDC and NIOSH. I'm on the Construction Sector Council and Hearing Loss Prevention Council, as well as the COVID-19 work group within the CDC NIOSH, as well as the Training and Education Committee within the Institute of Hazardous Material Management, Hazmat Society. We'll look at the agenda here, what we're going to try to cover today. So we're going to look at some recent fatalities within confined spaces. I know we got people from across the world that are in this webinar today and this virtual training. So these are just going to focus on the ones that are in the United States. But again, hopefully you'll be able to apply the lessons learned to your organization and help make these preventative measures. So we're going to look at recent fatalities within confined spaces. We're going to discuss the hazards associated with entry operations. We're going to cover the basics. We're also going to go into a little bit more detail on the technical aspect. We're going to evaluate emergency rescue services. This is one of the things I'm going to hone in pretty big on. Just coming from the background of emergency services and coming from a confined space rescue technician standpoint, there are some things that a lot of employers across the United States and across the globe maybe misunderstand about emergency services and their capabilities. So we'll talk about those, discuss various types of hazardous atmospheres. We'll have a few, back up here, we'll have a few situations to where we'll have a interactive session to where you can be the judge on whether you think it's a safe atmosphere or not. We'll have that a little bit later on, and then we'll discuss asphyxiants and how they affect safe entry operations. And as you'll see, asphyxiants will be one of the major factors in our atmospheric monitoring. Moving on to one of our first examples, or one of our first scenarios recently was in December of 2019. So right at the end of last year, there was 2 workers that were killed when they went inside of a tanker truck at one of their Texas chemical plants. So as you can see here, they went into a tank that had some residual chemicals left over. And again, we're just keeping the concept as broad as possible. So even though this says vinyl acetate polymer residue, this can be any chemical that you can think of. This can be a gasoline tanker that has a flammability hazard. This can be a tanker with hydrogen cyanide. It can be vinyl acetate polymer that you see here. There's a lot of different things that you can have here. So we're just basing on the principles. So the first employee went inside the tank to clean it out. Employee number 1 became unresponsive. Our natural reaction, our natural instinct as a human being is we see somebody go down, we want to jump in there and get them out. We naturally want to help our friends out, help our coworkers out. Sometimes these coworkers are friends, sometimes they're family, but we want to jump in and we want to help them out. So second and third coworkers jumped in to rescue them. They also became unresponsive. Employee number 4 into the tank was able to rescue number 2. You can see that they had some signs and symptoms of chemical exposure. And so just based on the severity of the exposure and the length of exposure, this ended up claiming this ended up claiming 2 lives from that incident. 5 other employees that were involved in the rescue attempts were also exposed to the chemicals. So that means the fire department, the rescue services were also exposed to the chemical exposure. And this company was ended up cited by OSHA for 10 violations, almost $500,000. As you can see here, the three standards they cited them for was respiratory protection, confined space, permit required confined spaces, and hazard communications. So 10 violations ended up totaling almost $500,000, certainly preventable. What we're going to look at here today is you'll start to see a trend in these case studies. I'll skip to the next one here to where you can see kind of the same scenario. But we're going to start seeing is a trend of people that are going in after their coworkers, going in after their friends to try to get them out, and they're becoming a victim themselves. So here's a second case study, actually in Houston, Texas, so right down the street from the last one. This was in July of 2019. So they had a hydroseeder spreader truck at one of the local high schools. Again, the first worker went on there, just simply opened the lid of the tank truck up, and the fumes came out, overcome the worker, caused him to fall inside the tank just because he came unresponsive and unconscious. Second worker, again, same scenario. Second worker goes in, tries to get him out. That person collapses, and both of those workers were actually pronounced dead at the scene. So fire department arrived, they put on their SCBA, their personal protective equipment, and could not get them out. Moving on to the third case study here. This one was a few years back in 2017 in Key Largo, Florida. They opened a manhole cover, 15-foot deep drainage ditch. First employee went down, became unresponsive from hydrogen sulfide and methane exposure. And then you're going to start to see the exact same things here where their would-be rescuers will go in and try to save them out. And there was actually a firefighter that lost consciousness once they arrived on scene for whatever reason. And I couldn't find the details on it, but for whatever reason, the firefighter took their SCBA off, their respiratory protection off to try to get through that manhole cover, and they were exposed to the chemicals. But just because they were the last one exposed with the least amount of exposure, they were able to be placed in an induced coma, and they were able to survive. So again, with this one, 10 serious violations, over $100,000 worth of citations. So moving on, if you haven't looked at OSHA's website, you can look at their website. They'll have what they call a CAT-FAT report, which is catastrophes and fatalities. And you can search within the recent years. You can go in there and search whatever event, whatever hazard that you're curious about. And as you can see here, I pulled this screenshot up. I typed in under the hazard description, I typed in confined space, and it pulls up everything that deals with a confined space that OSHA knows about. And so you can see a trend that I put the arrows by. 2 workers in confined space die from exposure to hydrogen sulfide gas. Worker asphyxiated inside a confined space on 3 of those. And then the last one, 3 workers asphyxiated from exposure to hydrogen sulfide. And so you're really starting to see a trend here with the asphyxiation. And what that means, asphyxiation, if you're not familiar, asphyxiation is being not able to breathe for a number of different reasons. And so if you're curious about this, again, you can go to OSHA's website. It's called a CAT-FAT report. Their catastrophes, fatalities report. You can type in whatever hazard. If it's falls, or if it's confined space, hazardous materials, you can type that in the hazard description, and it'll pull up every case that's related to that topic. So pretty good information there. Now this is what's startling to me is the confined space statistics. So since 2017, again, in the United States, there have been at least 15 fatalities from confined space entries. Now these are just the things that OSHA knows about. This may not include things that are occurring on private property. Maybe they didn't deem it a confined space fatality. Maybe they said it was a fatality for some other reason, but it didn't get classified as such. But just based on these 15 fatalities related to confined space entries that OSHA knows about, 10 of those, so 2/3 of those, were due to asphyxiation. So that's the issue we're going to focus on today. 3 of those died during a fire, and those were actually during the same event. 1 died from a fall within a confined space, and then 1 died when they're from a respiratory arrest. Their lungs stopped working. So again, you can see 2/3 of these fatalities are due to asphyxiation. So you're starting to see a common trend here. Moving on to the factors in confined space fatalities, we're going to break these down individually, look at some things that maybe can apply to your workplace, maybe some things that are applicable to all industries. So the first one here is look at is failure to recognize a confined space. So they don't recognize that it's a confined space from the beginning. So if you look back at OSHA's definition of confined space, it's large enough to make bodily entry. It's not designed for continuous employee occupancy, and you can get inside of that space and perform work. So they don't recognize confined space, or they don't recognize the hazards involved with that entry. So maybe they weren't aware that there is an engulfment hazard or an entrapment hazard within that confined space, and they forget to mitigate those hazards. If there was an engulfment hazard, maybe they should have blanked the line. Tendency to trust our physical senses. This is something that's huge for me. I hear a lot of people that will give me the reasoning about, will specifically mention hydrogen sulfide, H2S. If you deal with hydrogen sulfide, H2S, it does have a almond smell, but that is only at certain parts per million, at certain levels. And so what you will find out is that up to 100 parts per million, you can smell that burnt almond or that smell that's associated with the hydrogen sulfide. However, once you get above 100 parts per million or around that area, it will actually kill your olfactory nerve, which is your sense of smell. And so that gives us the false sense of security. Well, I'm not smelling anything. Well, if you get exposed to a high dose right off the bat, maybe it's killed your sense of smell and you're having that false sense of security. So again, physical senses should never be used as a way of determining what hazards are inside the workplace. Moving on to the fourth one, underestimating the danger. And this, I'm going to go ahead and bring the next one up as well, because they're kind of tied hand in hand. Underestimating the danger and complacent attitude. And so to me, those go hand in hand. It's if you underestimate it, well, I've been in this space 20 times, or I'm just going to be in there for a few minutes, it's not going to be a big deal. You get complacent, you think the hazards aren't as big of a deal as they are. You go into the space and then you get overcome by the chemical hazards, you get overcome by the engulfment and entrapment hazards. Maybe an agitator blade starts up and you get injured that way. So underestimating the danger and then being complacent about it. And then the last one here is attempt to save a coworker. We talked about this recently. Our natural instinct as a human being is we see a coworker go down. Our natural instinct is we want to jump in and get them out. This is something I personally had to retrain my mind on. I did 10 years as a firefighter with Louisville, Kentucky. My mindset at that point was our job is to run in and get them out of the confined space. So that was my mindset. But now that I'm out of the fire department, now that I am in a consulting role, in an EHS professional role, that's not my role anymore. My role is to figure out what that person went down from, notify the appropriate rescue services, and make a plan at that point. So attempting to save a coworker can cause 1, 2, 3 extra victims, whatever it may be. So those are some big factors within confined space fatalities. So moving on to the next one here, again, we talked about this earlier, it's important to understand what a confined space is. You can't always assume that just because a organization has confined spaces that they're going to label it as such and they're going to label it properly. So it's important for us to understand what the confined space is. So this is breaking it down to the basics. So this is straight out of OSHA's 1910-146. Large enough and so configured that an employee can bodily enter and perform the assigned work. If I can only stick my legs in there, I can't stick my whole body in there, or if I can stick my whole body in there, but I can't turn my wrench, I can't really move around, that would not meet that criteria. So I have to be able to get inside the space and do whatever work I need to be doing. Not designed for continuous employee occupancy, so it's normally doesn't have anybody inside of it. And then the third one here is limited or restricted means for entry and exit. And we'll talk about what that really means as far as the OSHA letter of interpretation here a little bit later. That's one of the things that I've seen probably one of the biggest levels of confusion with. But then you get into the permit required confined space. So this is where it's supposed to be labeled per the OSHA standards. And so it's a confined space that has one or more of the following characteristics. And as you'll see here, they have the word potential is highlighted or is underlined and in bold because OSHA likes to use that word potential. So contains or has a potential to contain a hazardous atmosphere. So it doesn't necessarily have to be there right at that point, but if there's a potential for it to happen later on, I need to identify that hazard and take the appropriate measures. Contains a material that has the potential for engulfing an entrant. Has an internal configuration to where an entrant can be trapped or asphyxiated by inwardly converging walls or by a floor which slopes downward and tapers to a smaller cross section. And we'll have a picture that comes up a little bit later on that. And then contains any other recognized serious safety or health hazards. So that fourth bullet, that fourth number there is kind of a catch-all statement because OSHA is not going to identify every single hazard that applies to every single organization under their jurisdiction. So they put that catch-all statement to where it's site-specific. If you have a hazard that's basically not otherwise recognized, you can capture it under that fourth number there. Contains any other recognized serious safety or health hazards. Now moving on into what is an entry inside of a confined space. I've had people argue with me on multiple occasions over, well, I'm just sticking my hand in there to get a meter reading, or I'm sticking my head in there to take a look. If any part of your body passes through that opening, passes through that plane that's in your confined space, that constitutes an entry. Now, if you look at this picture, it's a pretty fairly open space. If you look from outside the space before you make an entry, you can probably get a general idea of what's inside the space. But let's say this opening is in the bottom and there's very limited visibility. Well, I'm just going to stick my hand up there and get my atmospheric readings to figure out what the gases are. You may not know that inside that space, if you didn't do your hazard assessment, you reach inside that space and there's an agitator blade that's running, and you can either potentially get injured that way. Maybe you stick your head in there just for a second and you get overcome by those chemicals, just like with the tanker truck at the high school. We talked about the case study earlier, to where they opened up the lid, they became unconscious because the fumes hit them in the face and they fell inside the tank. Same situation here. So any part of your body, whether it's your head, your feet, your hands, any part of your body passes through the opening of a confined space constitutes an entry, and that makes you a confined space entrant, and you have to apply by all the OSHA regulations. So I'm going to bring up a picture here. A lot of people are not as familiar with what that third statement within the permit required confined space requirements that talks about inwardly converging walls. And so this is a picture of it's a mass flow bin at a chemical manufacturer. And as you can see, the point of entry is on that middle level. They have a square portal opening they can take off. They can enter that space, but if they fall down with those inwardly converging walls, it's going to be very difficult to get out without some kind of rescue service going on. So they can fall in that bottom space there. So that's the inwardly converging walls that they were talking about that tapers down to a smaller cross section. So if you haven't seen that, you see a lot of these mass flow bins at chemical manufacturers, but you see a lot of them at agricultural facilities as well. So several different applications, but at least you're understanding what the inwardly converging walls are. Here is just a few confined space examples. You've probably got a handful of different confined spaces at your facilities. This ranges anything from scrubbers to tank trucks, boilers and manholes, above ground and below ground storage tanks for that matter. Utility vaults, again, this is just a few examples. There are hundreds and thousands of different examples at your facility. So make sure you're evaluating your spaces. Make sure you're looking at those three confined space criteria to see if it's a confined space to begin with. And then if you do identify it as a confined space, figure out if it should be a permit required confined space so that you know what precautions to take. Minimum contents of the permit. We'll discuss these briefly, but I'm really going to focus on 9 and 10 here. So permit space to be entered. These are all the required contents of the permit based on OSHA's 1910-146. So I'm going to talk about the requirements. I'm going to talk about best practices as well. And so when you're getting to permit space to be entered, you need to be specific. So if I'm doing an annual evaluation of my confined space rescue program or a confined space entry program, if I look back at that confined space permit from 6 months ago, I shouldn't be able to tell exactly what space you were going into. And so if you're going into a silo and it has a number, put on there silo number 2 or mass flow bin number 4, whatever it is, some way to identify that space that you're going in so that you know exactly where they were at. Purpose of the entry, you can put related task on here. That's something a lot of people don't understand, is you can put related task. And what I mean by that is, let's say I'm a maintenance technician and I want to go inside this space, this underground vault or underground sprinkler pit, whatever it may be, and I'm going to go inside that confined space, inspect a valve, and if that valve needs replacing, I'm going to replace it while I'm in there. I don't have to make two separate permits, one for inspection and one for replacing the valve. I can put those on the same permit because they're related tasks. I can put, as my purpose for the entry, I can put inspect and replace valve, and that covers me on one permit. But if I'm doing two separate tasks, let's say I have a wide open wastewater pit that's 30 feet long to where I can have multiple operations going on. If I have multiple tasks going on and they're not related, then you have to have separate permits. And then on an additional note, rescue always has to have a separate permit no matter what. Rescue services can never piggyback off your permit. So purpose of the entry, they can be related tasks, but if they're not related, has to have a separate permit. Date and authorized duration of the permit. This is pretty self-explanatory, but make sure you're putting AM or PM. So if it's 12 to 8, make sure you're putting 12 PM to 8 PM or 12 AM to 8 AM, whatever it may be. That way we know exactly what time it is. And your organization needs to set a authorized or a limit on that. So what I mean by a limit is this permit cannot be used longer than 8 hours or 12 hours, whatever it may be. And what that does is it establishes a time frame so that when that time frame expires, so let's say it's 8 hours. So once your 8 hours is up, you need to pull everybody out of the space. If you're still doing operations, pull everybody out of the space, reevaluate the hazards, and fill out another permit. So it keeps you from getting complacent and maybe getting used to those hazards within a space. Authorized entrance, attendance, entry supervisor, and one of the things within OSHA requirements is you have to have a space for the signature of the supervisor as well. So entrance and attendance, you can print or sign their names, but supervisor has to print and sign both on that permit. Hazards of the permit space, and then how you isolate those hazards. So is there an engulfment hazard? Is there electrical hazards? Is there an entrapment, chemical, noise, whatever it may be? And then what are you doing to mitigate those hazards? I've found as a best practice, it's not required, but I've found as a best practice is to, when you do your hazard assessment on your confined spaces, make a list of those hazards that are in your confined spaces, list those out on the permit so that when they're making entry, when your employees are making entry in that confined space, they don't have to sit and think of off the top of their head, what are the hazards inside of that confined space. They can look at this list and just check off the box on what hazards are inside of that. And then you can also put a space where they can list out anything that's not listed. But number 9 and number 10 here, acceptable entry conditions. So what I mean by that is when you're getting to the atmospheric monitoring part of your confined space operations, what is acceptable for oxygen content? What is acceptable for your explosive or combustible content? What's acceptable for your carbon monoxide, hydrogen sulfide? And so again, it's not a requirement, but it's a best practice to go ahead and put those acceptable limits on there. So you have to be able to determine, okay, within OSHA standard, oxygen content must be between 19.5% and 23.5%. Go ahead and put that on there so where they don't have to think about it. They know exactly what those acceptable limits are, and they know if they're outside of those limits, then it's a no-go for the operation. And then results of the initial and periodic tests, names or initials of the testers, and when the tests were performed. This is going to be something site-specific based on every operation you make. OSHA just tells you that you have to make initial atmospheric monitoring and then periodic based on your hazard assessment. And so we'll talk a little bit more about that later on what periodic actually means. Rescue and emergency services, who are you relying on to come get you if something goes wrong? If you go down inside that space and you collapse, whether it's a medical emergency or whether it's from an atmospheric hazard, whatever it may be, if you need to be rescued, who's going to perform that rescue? Communication procedures, how am I communicating from outside the space to inside the space? So that could be verbal, that can be simply talking to them, that can be using a handheld two-way radio. Whatever method you're going to communicate with that person inside the space is what you need to put on that permit. Equipment, whether it's PPE, your personal protective equipment, your testing equipment, have that all listed on there. And where this is going to play into a factor as well is especially with your personal protective equipment, is if a rescue needs to be needs to be initiated, those rescuers have to at least have the same level of PPE that you put on your permit or higher. A lot of times when they do a confined space rescue, they're going to throw on a self-contained breathing apparatus as a best practice, regardless of the situation, just to be a proactive and as a best practice to make sure they're not getting any atmospheric hazards. And then 14 is any other information necessary in order to ensure employee safety. So a lot of times what I'll see in this section is the entry and exit time. So what time did entrant 1 go in? What time did they come out? So I know how long they've been exposed to the various hazards within a confined space. So moving on is, where is your closest rescue team? This is something to get you thinking about, where is your closest rescue team to your facility? Is it right down the street? Is it 20 miles away? And then are they capable of that rescue? And so this is a drill that I did several years ago with a few local fire departments on their confined space rescue. So you can see it gets pretty intricate when they perform a rescue operation. So they can make it as intricate as you see here. You can have your own internal rescue team if you have the staffing and the availability to train your own internal employees to be rescue technicians. Then that's great. That helps your employees out. That has somebody on site. But what I want to point out here is always verify your local fire department. If you're going to rely on your local fire department to make that rescue, make sure that station, that fire station, that firehouse, that fire department close by you is not only trained, but also staffed when you need them. There are a couple of things on OSHA's, on their websites, and I'll pull it up here in a second to show you, but most people will assume that fire departments can provide rescue services 24/7. That's not the case at all. 75% of the fire departments in the United States are all volunteer, which means they're not there at the station. Even within Metro Louisville, Kentucky, where I was working at, there were stations that were staffed all the time. The ones I worked at, we were staffed, worked 24 hours a day, 7 days a week. But there were also stations that were not staffed. Maybe it was a third station or a substation that was only staffed by volunteers whenever they were off work from their normal jobs. But then you also get into the situation of, okay, they're staffed and they're trained, but is the rescue apparatus their normal, what I call daily driver? And what I mean by that is, so let's say an engine company, firefighters are normally driving out on the engine company or the truck company. And if you look at the picture here, the truck company is the one with the ladder, the engine company could be either one on the right or the left side there. But if that's their daily driver, that's the one they go on all their runs with. But let's say they have a second apparatus that's in the station that they use for rescue services only. Well, let's just have a situation where they're out at the grocery store, they're getting their groceries for lunch and dinner, and they get called out to a confined space rescue. If that's not their daily driver, if that's not if that's not the apparatus that they drive day in and day out, that means they're going to have to leave the grocery store. They're still going to have to go back to the firehouse, switch everything over to that rescue apparatus, and then respond. So you're having that big delay on your rescue times. So if you're going to rely on the local fire department, call and verify they're staffed. But the best practice is always to have a rescue team on standby directly at the site. I'll pull up a slide here that'll tell you a few of the requirements within OSHA's regulation here. So just 1 second, we'll switch screens. Let's see here. All right. And so here is one of the requirements within OSHA's 1926-1211, which is the construction industry's confined space regulation. And so as you can see here in 1926-1211 A3 III, the rescue service agrees to notify the employer immediately in the event that the rescue service becomes unavailable. So that means that if I'm relying on the fire department, they are agreeing that they're going to call you as the employer and let you know that they're unavailable. I'm going to tell you that's not going to happen. From somebody that's been on a fire department, if we get called out from a fire department, we get called out to a medical call or a car wreck, whatever it may be. Our first thing going through our mind is not to call company XYZ and tell them we can't do their confined space. Our first thing on our mind is to go to that emergency call that just got dispatched. And so I want to tell you that even though it's the requirement, probably not going to happen in real life. Now, even though it's a requirement, you may have that situation under an agreement, from a fire department perspective, that's probably not going to happen no matter where you're at, whether it's a volunteer department, whether it's a staff department. Where this is going to most of the time apply to is if you have on-site rescue services. So you hire out a third-party contractor to perform your rescue services. So again, if you're relying on fire department, per the construction industry standards, they're required to tell you if they can't do it. But I'm telling you, it's probably not going to happen. Now I will switch over to the 1910-146, which is the general industry standards. And so what this puts in here is it does not have that same requirement. It does not say they have to make that notification. They have best practices. They have an appendix, I believe it's Appendix F, that will have ways that you can evaluate a rescue service on how efficient they are. But what this comes into is employee participation. So 1910-146 L1, employees shall consult with the affected employees and their representatives on the development and implementation of all aspects of this section. So what I recommend to employers is I use this as a reference, but I will recommend to employers ask the employees that are making the entries inside the confined space, are they comfortable waiting on the fire department to get there? Are they comfortable with X, Y, and Z, whatever company you contracted out to get a confined space rescue service going? You have to get them involved and make sure they're comfortable and at least have a chance to review that. But again, you know, this is probably one of the biggest areas that people misunderstand from an industrial standpoint, is that most of your fire departments are not staffed 100% of the time. Maybe they're staffed, maybe they're staffed and they're trained, but maybe they don't have the equipment. I've ran into this in previous situations to where there are, let's say there's 6 fire stations within your city, your jurisdiction. There's 6 fire stations. They're all trained. Everybody at each station is trained on confined space rescue technician levels, but only one of those stations has the equipment to make the rescue. So now you're waiting on, well, which station has the equipment? Now you have to determine that when you're making your hazard assessments. So always verify your local department. So we'll switch back here to presentation. So hopefully that makes sense. Again, we can talk about it more a little bit later on if you want to discuss that. So again, what does the OSHA standard require? Within OSHA's 1910-146, the general industry standard, you have to designate a rescue and emergency service that has the capability to reach the victims within a time frame that's appropriate for the space hazards identified. So this leaves it up to you as the employer, you as the organization, on determining what that time frame is. OSHA does not come out and say they have to be able to respond and be there in 3 to 5 minutes. They don't come out and say you have to be there within 10 minutes or whatever, 3 miles away, whatever it may be. You have to make that determination based on the biggest hazard, or the hazards identified within your confined space. If you do your hazard assessment and your biggest hazards are simply a fall from a ladder and maybe a broken bone or a broken leg, that's not as pressing of an issue as if you're going into a confined space that has chemical hazards, and now you're dealing with asphyxiation hazards and situations that are IDLH, or immediately dangerous to life or health. Those are going to be a little bit more pressing of an issue, and you need to have a quicker response. If you have an IDLH atmosphere, one that's immediately dangerous to life or health, you have to have somebody that's trained on confined space rescue procedures. You have to have a rescue team on site. And that is actually referenced within the OSHA's Respiratory Protection Standard, 1910-134. They tell you that anytime there's an IDLH atmosphere, you have to have rescue personnel on site ready to go as soon as you need them. So again, that comes back to the employer, your organization, on determining what that time frame is. Yes, we want somebody as quick as possible. As a best practice, my best option is to have somebody there on site ready to make the rescue as soon as I need them. But if you can't make that, if you don't have that as an option, you don't have the resources to make that available for your employees, make sure you're properly evaluating your fire department, your rescue service, whoever you're going to use for that rescue operations. So here I'm going to give you a sample scenario for a typical confined space rescue. And this is based on my years of experience as a confined space rescue technician. I've looked at previous call records and previous response times within our jurisdiction to kind of base this off of. But as you can see here, we're going to start the time to complete. We're going to start the time frame at 0 seconds when that person goes down. So let's say the person collapses inside the space, they get overcome by anhydrous ammonia, or you can use whatever hazard you want to use at your facility. But let's say that entrant goes down inside the space, they collapse, that starts your time frame right there. Now the entrant, unless they're sitting there watching them, let's be honest, people don't watch inside the space 100% of the time. The attendant notices the entrant goes down. There's probably a 5-second delay in that. They're going to call 911 and talk to the dispatcher. There's probably about a 3-minute time frame on that. That gives the attendant time to talk to the dispatcher, tell them what the emergency is, where it's at, what the situation is going on, and provide all the necessary details. So at that point, you're at 3 minutes already. 911 dispatcher, they notify the fire department. That's about another minute. Fire department response from the station. That's a 2-minute time frame there. 2 minutes is kind of the standard for fire departments to get notified and then respond. And then arriving at the scene. This is probably where the biggest fluctuation may be. Is I'm going to put arriving at scene within 5 minutes. So if you're in a very rural part of your area, your jurisdiction, and maybe at that time maybe 20 minutes, or you may be fortunate enough to have a fire department or rescue service that's right down the street, and that time maybe 1 minute or 2 minutes. So that's going to fluctuate based on your location. So we're going to put five minutes for this situation here. Once they arrive on scene, they have to go to the exact location of this emergency, and they have to develop a plan of rescue, how they're going to get them out. They're going to fill out all their permits, come up with a game plan. That's going to take about 5 minutes to get all their equipment back to the scene of the emergency. Another 5 minutes to get the permit filled out, air monitoring complete, equipment set up. Now this is everybody working together. These are on a good day. These are everybody working together. One person is doing the air monitoring, one person's filling out the permit, a couple people setting up the equipment. This is not one person doing everything themselves. This is multiple people working as a team together. So about 5 minutes to get everything set up. Fire department enters the space, they assess the victim, figure out what's going on, what kind of treatment they need. About a minute, they stabilize the victim, get them out of the space. 5 minutes later, and then from the time they get them out of the space and get them ready and transported over to an ambulance to get taken care of, at that point you're about 28 minutes from the time that person collapsed to the time that person is at an ambulance and being given appropriate treatment. You're at about 28 minutes, and that's just a sample scenario. So if you're dealing with, let's say they have a medical emergency, let's say they have a cardiac arrest. For those of you not familiar with that, every minute that you're in a cardiac arrest, it's estimated that you lose a 10% chance of survival. And so if you do the math on that, after 10 minutes, you're basically deemed non-revivable after 10 minutes of no medical care. So 28 minutes is a pretty big time frame here. But I will bring up this case study next here. And so there was a case study by California's OSHA back in 2012. And so what they did was they reviewed hundreds of calls, hundreds of confined space rescue responses over a period of a couple decades. And what they found out was the average arrival time. So that's the time that fire departments were dispatched to the time they got to the scene of the emergency, was 5 to 7 minutes. And then the average rescue time was 48 minutes to 123 minutes, so a little over 2 hours. And so again, that 28 minutes scenario we just talked about that's on a good day. That's when everything is going perfectly fine and everything's going great. But the average rescue time here, based on these studies, was 48 to 123 minutes, so a little over 2 hours. And then you see the caveat below that, whenever there were hazardous materials involved, that rescue time changed to 70, so a little over 1 hour, to 173 minutes, which is almost 3 hours. So just imagine in your mind having to take 3 hours to get somebody out of a confined space. If you're dealing with an exposure to a chemical, unless they're wearing respiratory protection, they're probably not going to last that long. Just being honest here. 123 minutes, 173 minutes are extremely long periods of time, 2 to 3 hours long. If you're the one inside that space that's waiting to be rescued, it's going to seem like an eternity. But again, this is where the best practice of having somebody on site ready to do the rescue as soon as you need them. That's what I'm highly going to recommend for that. Even if they get there, the arrival of 5 to 7 minutes, even if they make that arrival time 5 to 7 minutes, doesn't mean they're going to go in and get you out within that time frame. That's just getting to your scene. And so I've got the reference here. Again, everybody will get a recording of this afterwards, so you can pull up that this case study and review the results. But I thought that was some pretty interesting statistics. of how long, actual rescue will take. So now we're going to get into the good part. It's the hazardous atmospheres in confined spaces. And so atmosphere that may expose employees to the risk of death, incapacitation, impairment of ability to self-rescue, so they can't get out on their own, injury, or acute illness. So we're going to focus on that acute part here in a second. Acute illness from one or more of the following causes. So your oxygen content drops below 19.5% or goes above 23.5%. Your lower explosive limit or your lower flammability limit, LEL, LFL, whatever you want to refer to it as, is going above 10% for that flammable gas, vapor, or mist. Your airborne combustible dust is at a concentration that exceeds its LEL. And OSHA actually has a letter of interpretation that says you can approximate what that condition is, the combustible dust. You can approximate that by a point where you can no longer see or having obscure vision at 5 feet or less. Atmospheric concentrations of any substance in excess of its published dose or PEL, which is permissible exposure limit, or any other atmospheric condition that is immediately dangerous to life or health. Now we're going to focus on a couple things in this section. So one of those I mentioned earlier is the acute illness. Acute means short-term, right? Short-term, high dose. So that means I want to get exposed to it right now and have issues with it right now within the next few minutes. To whereas chronic illness is long-term. Maybe I'll have illnesses. Maybe I'll develop symptoms a year from now. So this is focusing on the acute illnesses that happen right now and very short-term. But then also we're going to look at this permissible exposure limit, the fourth bullet point. Atmospheric concentrations of any substance in excess of its published dose or PEL. So I'm going to show you here a letter of interpretation from OSHA back in 1999. It's still current. It's still their current interpretation. So what this person asked OSHA, they said, is if a confined space has an atmospheric concentration of a contaminant over the permissible exposure limit, over the PEL, but it's not capable of causing death, incapacitation, impairment, the ability to self-rescue, injury, or kill illness, would this meet the definition of a hazardous atmosphere? And so what OSHA came back and said is that basically you're looking at the acute illness portion of that contaminant. So it says that the confined space standard clearly states that an atmosphere that contains a substance exceeding the PEL is limited solely to prevent long-term effects, is not considered to be a hazardous atmosphere on the basis alone. So they said, therefore, if the atmosphere is above the permissible exposure limit, it does not automatically make it a hazardous atmosphere. And so the one that comes to mind for me is asbestos. So I don't know if any of you deal with asbestos at your workplace or have dealt with asbestos in the past. Asbestos has a permissible exposure limit, it has a PEL. But if I have that inside of a confined space, that asbestos is not going to kill me or injure me or cause an acute illness. It's going to cause issues 20 years from now when I get mesothelioma or some kind of lung cancer from that asbestos exposure. So with that in mind, that asbestos, simply having that asbestos inside that space is not going to deem that space a hazardous atmosphere because it's chemical in there. It's not going to cause issues now. Now, do I still need to take best practices? Do I still need to minimize and mitigate to the least amount possible, minimize my exposure? Absolutely. You don't want to get exposed to it any more than you have to. But what they're saying is just because it's over the permissible exposure limit does not necessarily make it a hazardous atmosphere. And so take that into consideration when you're making your hazard assessments. And speaking of hazard assessments, you're required as an OSHA requirement is to assess each space within your organization and have some kind of documentation on what the hazards are within that space. So this is one that I've created for a customer site. And so they had an Excel spreadsheet. Actually, we're still working on it right now. That's the one you see the yellow highlights on. But we created it for a customer site, but it has their space ID. And so again, if we're talking about our permit, we're talking about the space to be entered. What we put there is HT1 or R30 or RMT 101, and I could put the space name. So if I put HT1 compressed air holding tank, that's what I would put for a space to be entered. Now it puts the location. If you're not familiar with the facility, I can break this spreadsheet down onto, T4 or 41 building or tank farm. I can break it down into all the spaces that are just in different areas. This one goes into detail about the different floors it's on. At the time, this is telling me as a consultant, is it labeled or not? So the ones that are in, it tells me it's not labeled like it should be. Y means it is labeled. Permit required, the ones with the X's on the atmospheric hazards tell me which ones I should be monitoring for. So should I be monitoring for oxygen, carbon monoxide, hydrogen sulfide, or the LEL, engulfment, so on and so forth. You can see those there. And what we went ahead and put on the capacity portion of the last one is how much, what's the holding capacity of it. So these were all liquid chemical tanks. And so how much chemical will that tank hold? So it could be anywhere from, as you can see here, from 460 gallons at the bottom to 25,000 plus gallons of chemical. So it gives us a good idea of what's inside the space. So air monitoring within the confined spaces. We talked about this a little bit earlier, is atmospheric testing shall be conducted. Again, shall means you're required to. So shall be conducted prior to initial entry. So before anybody goes in, I have to do atmospheric testing to figure out what's inside the space. And I have to do it periodically thereafter. And so that periodically, what we're discussing earlier is periodically means is based on your hazard assessment, based on your site-specific situation. And so I'll give you a couple of examples. And so if I have a confined space and I do my initial air monitoring and all of my measurements come out good, I've got 0 carbon monoxide, I've got 0 on my hydrogen sulfide, my oxygen content is 20.8%, and it's reading well, and my LEL reading is 0%. If those all come back great on my initial reading, my recommendation for a best practice is for periodically is every hour at the most. But let's say you do your initial entry, or I'm sorry, your initial air monitoring, and you have high readings right off the bat. Your first readings were, let's say your carbon monoxide was 30 parts per million, your hydrogen sulfide is 20 parts per million. Your readings are above what they should be. And you have to do ventilation, you have to take proper precautions to get those levels down. If I have high initial readings, I'm probably going to do periodic readings more often. So rather than every 60 minutes or every hour for periodically, I may reduce that to every 30 minutes or every 15 minutes. So why do we need to test the air? We need to evaluate the hazards inside the space. I need to figure out what is it that's inside that space. So is it hydrogen sulfide? Is it carbon monoxide? Is it anhydrous ammonia? This will all be based on your site-specific hazard assessment for your confined spaces. So I evaluate what's inside the space, and now I need to verify that whatever is inside the space is in with the acceptable range. So is my oxygen content between 19.5% and 23.5%? Is my hydrogen sulfide content below 10 parts per million, so on and so forth. Once I understand those, I'll come up with some kind of game plan on how to control those measures. So do I need to have ventilation? Do I need to have forced ventilation? Am I doing negative pressure ventilation? Am I doing positive pressure ventilation? So I'm not going to get too detailed with that, but you need to figure out what kind of controls you're going to implement. And then make sure that your continuous forced air ventilation is actually doing its job. So just because you throw a confined space fan inside your confined space and you're doing negative pressure ventilation, just because you have that fan there doesn't mean it's doing its job. You have to continuously evaluate to make sure that those levels are staying acceptable. And so that's where your periodic evaluation of your atmosphere is coming into play. So where can I also get toxic atmosphere? So not only from, we talked about chemical tanks before. Sure, you're going to have chemical hazards from the chemical tank itself. So the product stored inside the confined space, you may have gases released when you're doing cleaning, materials that are absorbed into the walls of the space, or decomposition of the materials, but also if you're doing adjacent work in the confined space. So let's say you're doing welding inside the confined space and your welding is now producing extra fumes that you have to be aware of. Painting, scraping. I had a contractor that was using a resin to coat the inside of a above ground storage tank, and that resin was producing high toxicity levels. And so just having that they initially had the 5-gallon bucket in there. Once I saw that, I said, let's get the 5-gallon bucket of the resin outside of the space so that you're not being exposed to it inside the space. So sealing, bonding, melting within areas adjacent to a confined space. And what I mean by that is anything that's in the remote proximity of that space that can cause an issue. So maybe there's a work truck that's sitting right next to the space and they're sitting in the truck. It's getting close to wintertime. They're turning the heat on, they're running the truck, and it's pumping out the exhaust fumes inside that confined space. So now you're getting your carbon monoxide. So be aware of that. Now I want to give you a couple examples here. 2 different meters. You can use whatever meters you want, but I just want to show you the variances from meter to meter. And so the one on the left side is an MSA Altair 5X. The one on the right side, the yellow one, is a RAE MultiRAE meter. But one important thing that you need to look at when you're doing atmospheric monitoring is your T90 response time. And so what T90 response time, what that is you can find this in your owner's manual for your gas meter. But what that means is how long does it take for that sensor inside your meter to get a 90% accurate reading. And so we're going to look at the MSA on the left side. So for the oxygen sensor, you should, according to the manufacturer, should have a 90% accurate reading within 10 seconds. Carbon monoxide is within 15 seconds, hydrogen sulfide within 15 seconds, and then combustible explosives, your LEL, is within 10 seconds. Now, if you look over on the right side of your RAE MultiRAE meter, your oxygen has a T90 response time of 15 seconds, but if you look at your carbon monoxide and your H2S, your hydrogen sulfide, they have a T90 response time of 35 seconds. So it's quite a big jump there. Now, even though these sound remotely small, if you went back 5-10 years ago, I'll give you an example, there was a meter that was called an MSA Passport. Some of you all may have used it in the past, some of you may be familiar with it, but I was contacted by a company. They wanted me to do a training on air monitoring training on a MSA Passport. And so I looked up the specifications on it. The T90 response time they were using it for anhydrous ammonia. So the T90 response time for anhydrous ammonia sensor on an MSA Passport, which is a meter that was made over 10 years ago, was 300 seconds, which is 5 minutes. And so even though these times here seem fairly small, they've come a long way. But also you want to keep in consideration if you're using tubing. And so this one on the left, the MSA meter you see does not have an option for tubing. So you can't do the old trick of tying your meter up to a rope and dropping it in space, pull it back out real quick. But if we're going to use this RAE MultiRAE meter on the right, I'm going to attach tubing to the top of it where you see that gray filter. If I attach tubing to that, I need to look in my operating manual for that meter to determine, one, the maximum length and the added response times. So the maximum length is important because your pump inside your meter will only be able to pull air so far. And so maybe it says your maximum length of tubing is 50 feet. What that means is if I put a 75-foot tube on there, it will not have enough power, enough force to bring that contaminant back 75 feet to the meter to process it. So you won't get an accurate reading. And then your added response times. So these T90 response times are your baseline, but if I'm adding tubing, I need to know how long it takes for that meter to pull the contaminated air through the tubing back to my meter and process it. So there's kind of an industry standard that you add 1 second per foot of tubing, but you need to consult with your operating manual because they're all different. Sometimes it may take 1 second per foot. Sometimes it may take 3 seconds per foot. So we're going to use an example of 1 second per foot. Let's say I'm using this MultiRAE meter on the right side, the yellow one, and I'm going to have 20 foot of tubing on there. And if I'm using a 1 second per foot guideline, that means I add 20 seconds to every one of these sensors. So that means my hydrogen sulfide, my carbon monoxide, it's going to take 55 seconds, so almost an entire minute to get a 90% accurate reading. And so if you're going off of OSHA's guidelines for atmospheric testing, they recommend testing every 4 feet in vertical spaces. So what that means is if I'm in a vertical space and I'm dropping a tube down from the top, they recommend dropping your tube down at 4 foot increments, taking a measurement, dropping it down 4 more feet, taking another measurement. And so that means you need to wait for that proper response time before you drop the tube down. You have to give your meter time to react, your meter time to process and gather all that contaminated air and provide an accurate reading. If you're just dropping your tube in there for 2 seconds, pulling it back out, you're going to get your readings because you're not giving your meter time enough to process it and provide the accurate readings. So normal background concentration. So what is normal for you is going to be different than normal for me. If you're going to Denver, Colorado, to where their sea level they're a lot higher than sea level in most of the country, they're going to have different oxygen content. But normal oxygen concentration, as an industry best practice, normal oxygen concentrations are going to be between 20.8 and 20.9% of oxygen, depending on the type of meter you have. Now, MSA meters will typically read 20.8%. RAE meters will typically read 20.9%. I'm not worried about the 0.1%. If I start seeing a 1% drop, that's when I start worrying. But the 20.8 to 20.9, if I start seeing fluctuation between there, I'm not that worried about it. But when I initially started at 20.8 and then an hour later I'm at 19.8, That's when I need to be figuring out what's going on. So normal LEL readings, your combustible explosive readings, should be 0.0%. OSHA gives you the guidelines of 10% maximum on your LEL. For air contaminants such as carbon monoxide and H2S, hydrogen sulfide, check with your host facility because sometimes you may be in a situation to where a little bit of hydrogen sulfide may be naturally or maybe normal. And so you go into a basement or a pit, sometimes you may see warning signs that tell you there's hydrogen sulfide present. And so you go into a pit in the basement and you figure out what that is. Maybe it's normal to have 2 or 3 parts per million background, but understand it before you go in. And so we just talked about your acceptable limits. O2 must be between 19.5% to 23.5%. Your LEL must be below 10%, but ideally it should be close to 0% as possible. Carbon monoxide should be below 35 parts per million, and H2S should be below 10 parts per million. But again, as close as I can get to 0 is the best. Now, these are the limits. If you have a meter that's used in the United States, these are the limits that are typically pre-programmed in your meter. If you buy a meter from the manufacturer, a gas meter, a lot of times they'll send you a CD or some kind of software that you can upload to your computer, and to where you can plug your gas meters in there and modify those acceptable limits. Now, I would not recommend at all. I would not recommend increasing those limits. But if you want to go more stringent, let's say you want to change the carbon monoxide limit from 35 parts per million, you want to change that to 25 parts per million. So that would be something you can do to make it more stringent. Moving on to vapor density here refers to how heavy or light a gas is compared to air. So we're going to use the concept that air is 1.0. So anything that has a vapor density less than 1.0, so we're going to give you the example of methane. Methane has a vapor density of around 0.7. So that's going to be lighter than air, so it's going to rise. It's going to ideally rise to the top under standard temperature and pressure. Now, chlorine with a vapor density greater than 1, it actually has a vapor density of around 1.9. So since that's greater than 1.0, it's going to ideally sink lower to the bottom. So we talked about the testing the 4-foot intervals earlier when you're inside vertical tight spaces, and this is the reason why. So you may have high levels up top and so-so levels in the middle, and then 100% acceptable readings at the bottom. So you want to make sure you're hitting all those levels to make sure you determine where those dangerous parts of the facility are. And whenever you're recording this on your confined space entry permit, it's a best practice to go ahead and document the worst case scenario. So what I mean by that is if, let's say I open up my space, I'm checking for hydrogen sulfide, and let's say I stick my meter in there, I drop the tubing down inside, my initial reading is 0 parts per million. I drop it down 4 more feet and I get about 8 parts per million. I drop it down 4 more feet and I get 16 parts per million. And I drop it down 4 more feet and I get back to 12, and then at the very bottom I'm down to 20. So you figure out what do I need to put on my entry permit. Put the worst case scenario on there. So if this situation, our worst one was 20 parts per million, so I'm going to put 20 parts per million on my entry permit under my air monitor results. What that does is allows medical responders and first responders, if something does happen to where you have to get a rescue situation going on, I know the worst. I know how much they could have potentially been exposed to. So I'm going to put the highest level on my entry permit. Moving on to LEL monitoring. And so this is something that I see a lot of confusion amongst people that are maybe they're not familiar with their gas meter, their portable gas detection equipment. And so LEL is lower explosive limit. Some people call it LFL, or lower flammability limit. So I'm going to use methane on here as an example. So methane's lower explosive limit is 5% concentration, and the upper explosive limit is 15% concentration. And so that's what you see as the red section on this line chart. So that methane will only burn within that 5 to 15% range. And so if you notice your meter, your gas meter, no matter what meter you have, it will tell you it's a percentage of the LEL. Your meter does not tell you the actual concentration of your chemical. It's telling you a percentage of that LEL. And so what that means is, let's say my meter says 1% LEL. That's what I'll look at it. It says LEL 1%. And so if I'm using methane as an example, how do I figure this out? Well, I take 1%, which is 0.01, multiply that by 5%, which is my LEL. So I'm trying to get 1% of 5%. And that gives me 0.05% concentration. So what this tells me is if I have if my meter says 1% LEL, that means if I'm looking at this line graph and it's for the 0 to 100, that means I'm at 0.05, which is barely above that left-hand section, right above, barely above 0. Now, 10% LEL is the legal limit per OSHA. And so what that means is if I do the same math, same calculations, I'll do 10% of 5%. That gives me a 0.5%, a half percent. So I'm nowhere close to that lower explosive limit, but I'm now at the legal limit. I can no longer make entry into that space. And so what they're doing is they're giving you a 90% buffer factor, a 90% safety factor to figure out what's going on before you get to a flammable atmosphere. They don't want you getting to the atmosphere to where it's flammable. They want to give you a heads up, a safety factor to figure out what's going on and make the appropriate recommendations. Now these next two, theoretically you should never get there, but just for the sake of for the mathematical portion of it, I do want to go through it. So if your meter said 50% LEL, again, it should never say that, but if your meter said 50% LEL, you would just multiply 0.5 by 5%, get 2.5%. And then if my meter actually said 100% LEL, what that would mean is I'm just now at that LEL portion. I'm just now at that 5% mark, and I'm now becoming flammable. So I wanted to explain that. I want to get that understood. So why will methane not burn at 30% is because it's too rich. And so anything to the right side of that UEL or UFL, whatever you want to refer to it as, anything on that right side is going to be too rich to burn. Now, it is important to notice that is under what they call STP, standard temperature and pressure. And so what standard temperature and pressure is a mathematical equation based on a temperature around, I want to say it's around 70 degrees. Don't quote me on that, but it's around 70 degrees and atmospheric pressure. So what that means is if my temperature changes, that methane, that 30% concentration may be a little bit different than what you're actually seeing. And so that's under STV, standard temperature and pressure. Hopefully that made sense for you there. So here is a safe or not safe situation. I'm going to give you three scenarios here. They're based on vertical columns here. So we'll look at the oxygen content. We're going to go from left to right. So if you look at this first scenario, your oxygen content, you're looking at your gas meter, it says 21% oxygen, it says 5 parts per million of carbon monoxide, your LEL says 0%, and your H2S says 0%. And so is it safe or not safe? We're going to go ahead with this, and we're going to say this one's safe. And then will the meter go off? Will the meter alarm? And for this situation, it's not, because it's all within the acceptable ranges. My oxygen, again, has to be between 19.5 to 23.5%. My carbon monoxide, my CO has to be below 35. My LEL has to be below 10%, and my H2S has to be below 10 parts per million. So based on those readings, it is safe to enter. The meter is not going to alarm. Now this second one here is where is going to have some explanations to it. So let's say that my oxygen is 20%, my CO and H2S are both 0 parts per million, and my LEL is 0%. Your meter is not going to alarm based on your set parameters because it's all within the acceptable ranges. But from my personal standpoint, I'm going to tell you that is not a safe situation. Unless you're in a situation to where you're in an atmosphere, let's say you're in a high altitude situation, or you're in an area that has a high altitude and your normal oxygen content is lower, that may be different. But let's say your normal oxygen content, back up here. Let's say your normal oxygen content is 20.9% or 21% roughly. And an hour later, I'm getting a 20% concentration. Why is that not safe? Well, something has to take the place of that oxygen. The oxygen does not just disappear. So even though my meter is not going off, my meter is not going to be alarming or vibrating, lighting up, whatever it may be, even though it's not alarming, I want to tell you that's not a safe atmosphere to go into. We'll talk about that more in a second, but the basis of you want to understand on that is oxygen does not just disappear, so you have to understand what is taking its place. And there's a slide coming up, we'll talk about that more in depth. But this last situation, this last scenario is 20.8 oxygen, carbon monoxide is 37, so that's already above the 35 parts per million threshold. Your LEL is 0%, your H2S is 1 part per million. So this one's a not safe. Your meter will alarm because your CO is above the threshold limit of 35 parts per million. So that was kind of a little bit easier one there. But if we want to get back to that second scenario, so why is 20.0 oxygen content not safe? So you gotta hang with me here. So in order to lower your oxygen content by 1%, so in order to go from 21% to 20%, there has to be 50,000 parts per million of an asphyxiant present. Some kind of unknown chemical. There has to be 50,000 parts per million of some unknown chemical that I have no idea. At that point, I don't have any idea what it is that's inside the confined space. All I know is there's an unknown chemical. There's 50,000 parts per million of it, and I don't know what it is. And so where do I get this 50,000 parts per million? So 1%, if you break it down, 1% is equal to 1% by volume is equal to 10%, or I'm sorry, I'm back up here, I'm trying confusing you. 1% by volume is equal to 10,000 parts per million. And so where do they get to 50,000 parts per million? Well, if you look at the atmospheric composition, oxygen is about 20.99%. So we're going to estimate that to be 1/5 of the atmosphere. And so whatever asphyxiant you have inside that space, we're gonna say it's carbon dioxide, CO2. That's a simple asphyxiant that displaces oxygen. So we're gonna say you have carbon dioxide inside your space. It's not gonna displace oxygen and then not displace nitrogen, argon, carbon dioxide, and neon. It is gonna displace everything. So that's where you get your factor of 5. So 1% by volume is equal to 10,000 parts per million. Since oxygen is 1/5 of the atmosphere, I now have to multiply that by 5 in order to figure out how much is actually in the atmosphere. So I multiply that 10,000 by 5, and that's where I get my 50,000 parts per million of some kind of asphyxiant. Could be a carbon dioxide, could be methane, whatever it may be. Something is displacing that oxygen, and I don't know what it is. So even though my meter's not going to alarm, my meter is not going to go off, my meter's not going to light up, it's not going to vibrate. Even though it's not going to happen, it's still not safe to make that entry. And so this is what I really want to emphasize today is understanding, even though your meter is not alarming, what is my meter telling me? My meter is telling me that there's something in there that a meter does not detect that I need to be aware of. So if I got this situation, I had 20.0 oxygen and it's normally 21% oxygen, I'm going to evacuate my entrance. I'm going to make sure everybody inside the space gets out until I can figure out what's going on inside that space, figure out what that asphyxiant is, and take the appropriate measures. Maybe I just need to do ventilation. Maybe I need to throw on some kind of PPE. Ventilation is best practice there. But I need to figure out what that asphyxiant is, figure out how much it is. And until I can do that, nobody is to go inside that space. Until I can verify the content, so what the asphyxiant is, and I can verify the levels, so how much of it's in there, nobody is to go back inside that space until otherwise authorized. So hopefully that made some sense. Hopefully it didn't confuse you. So moral of the story here is don't wait for your meter to go off before you exit the confined space. It can still be dangerous without ever going off. So again, what causes the oxygen to disappear? You're going to have 2 reasons here. So your reason is going to be either simple asphyxiants, which we'll talk about these here in a second. So either simple asphyxiants or your chemical asphyxiants. So simple asphyxiant, as defined by OSHA's Hazard Communication Standard 1910-1200, is a substance or mixture that displaces oxygen in the ambient atmosphere and can cause oxygen deprivation in those who are exposed, leading to unconsciousness and death. So basically, it's going to take all the oxygen in the atmosphere, and it's going to push it out of the room. It pushes it out of the room, and you don't have oxygen to breathe. There's no oxygen to breathe, period. Big thing about this is the simple asphyxiants do not require a GHS pictogram. So if you're following the GHS guidelines, as recommended by the United Nations, if you're following those GHS guidelines, you will not know it's a simple asphyxiant by looking at the pictogram, but you will often see a warning signal word, and you will find out through reading the SDS sheet, the safety data sheet, that it is a simple asphyxiant. So a couple of examples of simple asphyxiants. So again, these are things that just simply push it out, back up here, that push it out of the room to where you don't have oxygen to breathe, are carbon dioxide, CO2, hydrogen, methane, and nitrogen. Those are common ones there. Those are not all of them. There are certainly more than that. But these will push the oxygen content completely out of the room to where you don't have oxygen to breathe. Now, moving to a chemical asphyxiant. A chemical asphyxiant works a little bit differently. So what these are is it's an agent that prevents the delivery of oxygen from the bloodstream to the cells or disables the biochemistry of cellular respiration in the presence of adequate oxygen levels in the blood. So sounds like a lot of scientific stuff there. What it does is it keeps your body from using the oxygen. So there is still oxygen in the atmosphere, but chemical asphyxiants will prevent your body from being able to properly use that oxygen once you breathe it in. So carbon monoxide, hydrogen cyanide, hydrogen sulfide, are all examples of chemical asphyxiants. So I can still breathe in oxygen. If I have carbon monoxide in the atmosphere, I can still breathe in oxygen. That's why they call it the silent killer, is because if I breathe in a lot of CO, a lot of carbon monoxide, I slowly will get killed by it. It'll slowly kill me because it's still breathing in oxygen. You don't know any different until later on down the line, 8 hours from now, 4 hours, whatever it is, I'm no longer able to use that oxygen that I'm breathing in. So simple asphyxiant will simply push the oxygen out of the room. I can no longer, there's no oxygen to breathe. Chemical asphyxiants, I can still breathe the oxygen, but I can't use it properly. So looking at the health effects of asphyxiation, looking at the O2 by volume, so 19.5% is the minimum acceptable oxygen level per the OSHA regulations. Once you start getting down to the 15 to 19% range, you'll have decreased ability to work strenuously. So if you're normally doing a tough job, something that's normally hard to do, it's going to make it even harder. It's going to impair your coordination. 12 to 14% is going to increase your respirations, cause poor judgment. 10 to 12% is going to cause labored respiration. It's going to make it hard to breathe, and cyanosis of the lips, which cyanosis means it's going to turn your lips blue. 8 to 10% is going to start causing mental failure and fainting. Potentially cause nausea, vomiting, and unconsciousness. And then the 6 to 8% mark, possible recovery if you catch it within 4 to 5 minutes, but within 6 minutes, half your patients are going to be killed by that. And then it's 100% fatal within 8 minutes. And then 4 to 6% oxygen concentration within the atmosphere is almost an instantaneous coma, followed by death, unless you get that taken care of as soon as it happens. So moving on to, I'm getting low oxygen readings. Now what do I need to do? So I've got my meter out. Again, I'm getting, I'm getting a 20.3% oxygen content. This says if your oxygen levels drop by 0.5% or more, but all other sensors remain the same, here's what you need to do. You need to evacuate the space immediately. So get all the people out of that space. So there, and I've got the references are read to the OSHA standard that states this. So evacuate the space immediately, tell everybody within the space to get out, notify the entry supervisor and the host facility's EHS department, tell them what's going on. And then you need to figure out how that situation happened. How did that hazardous atmosphere develop? So I need to look at safety data sheets. I may need to look at confined space hazard assessments. I may need to look at my JSA, my job safety analysis, or my hazard analysis, figure out how that hazardous atmosphere actually developed. And then before anybody can go back in, I need to figure out how I'm going to protect employees from that hazardous atmosphere. So if I need to increase my ventilation, I need to increase my level of PPE, whatever it may be, before anybody goes inside that space, I need to put new measures in place to prevent that hazardous atmosphere from reaccumulating. And then after the entry operation is completed, discuss it with your organization. Use it as a lesson for everyone. Even though, let's say you have 20 maintenance workers or 20 people that go inside confined spaces, and only 2 people were affected by this situation with the hazardous atmosphere. Discuss that with your other maintenance workers. Discuss that with your organization so they can use that as a learning point and as a learning lesson to hopefully they don't run into it in the future, but if they do, they can know what the proper procedures are to take. And let's say you explain to them, this is how it happened, this is what I did to mitigate the problem, and this is how we completed the operation. So explain that, use it as a lesson learned from everyone. All right. So moving on, does anybody have, this kind of wraps it all up. Does anybody have questions? Those are all on here. Again, everybody will get a copy of a recording of this presentation. You will also get a certificate. But if you have questions, here's my contact information. If you think of something later on, you want to email me, contact me. Here's my contact information. You can email me, drew@aerosafety.us.com. You can go to our website if you were interested in our services. And then there's my personal LinkedIn and our company, Aero Safety's LinkedIn profile there as well. Again, we'll wrap up the recording. Unless anybody has questions, we will wrap up the recording. And I will send this out. You should have this recording by the end of the day. You'll have a certificate of training for that. Appreciate everybody's time. Appreciate everybody's participation. Have a great day, and I look forward to more trainings with everyone.